The final part of this differentiation topic is relative rates of change. Now what that means is we're trying to work out a rate of change, which is always in terms of time, how one variable is decreasing in terms of another. The way that we approach these questions is always the same, and I'm hoping that you'll figure that out over these next few examples. We're told that water is poured into a bowl at a constant rate of 20 centimeters cubed per second. So the first thing is to work out what that means in terms of maths. Well, centimeters cubed is a volume, so that means dV per second, that's per time, is 20. Now it's positive 20 because it's going in, and so that volume is increasing. We're asked to find the rate in centimeters per second at which the height of the water is increasing. So H, that is dH dt, is what when H equals 3. Now we're not going to use that H equals 3 until the very end, because if we set it now, we're now dealing with constants, whereas we want to be dealing with variables and then substitute H equals 3 at the end. So we need to write an equation for dH dt. And this is where the form dH dt as opposed to H dash has its advantages, because we can say dH dt is, well, that's going to be equal to dH over something times something over dt. And as long as those two current blanks are the same, they will cancel with fraction multiplication and we'll get dH dt. Now we already are told dV dt, so let's try and substitute dV into this too. Now we already know dV dt, so that's a tick. We just need to find this. In order to get dH dV, I need an equation for either H in terms of V or V in terms of H. Typically, it's actually easier to find V in terms of H, find dV dH, and then find the inverse or the reciprocal to get dH dV. Now we're already told what V is in terms of H, so that's nice and easy. I'm just going to slightly expand that, bring the pi out. That's 3 pi over 2 H squared plus 3 pi H, and differentiate. dV dH is equal to, bring the 2 in front, we get 3 pi H plus 3 pi. 3 pi's are common, leaving H plus 1. Now that's what dV dH is, so we want dH dV. That will be 1 over that. So it's 1 over 3 pi H plus 1. So now we have an equation for dH dt. That's equal to 1 over 3 pi times H plus 1 times by, and we're told dV dt is a constant 20. So this is an equation for dH dt at any height, and we want dH dt when H equals 3. So this will be 1 over 3 pi times 3 plus 1 times 20, or 20 over 12 pi. Both can divide by 4. We get 5 over 3 pi. Units are centimeters per second. You can give this as a decimal if you want as well, round to typically 3 significant figures. Question 2. The top of a 25-foot ladder leaning against a wall is slipping down at a constant rate of 1 foot per second. How fast is the bottom of the ladder slipping along the ground when the ladder is 7 feet away from the base of the wall? There's a lot going on here. It would be much easier if there was a picture. So here's my vertical wall, here's my ground, and here is my ladder. We're told that that is 25 feet, so ignore the units, that's 25. And we don't know how tall it is, so let's just give that y because it's going up, and on the bottom x because it's going across. We're told that it's slipping down at a constant rate of 1 foot per second, i.e. y is getting smaller at 1 foot per second. Because y is getting smaller, that means that we're told that dy dt is -1. Negative because it's getting smaller. We're asked how fast the bottom of the ladder slipping along the ground, so that would be dx dt is what when the ladder is 7 feet away from the base of the wall, so when x equals 7. Okay, so that's what we need. Now we can write our equation, dx dt, and we'll do the same as before. We're going to split that up and substitute a common variable into these two. Well, we know dy dt, so we're going to make this dy. We know this, we want to find this. To link x and y to get dx dy, we can use Pythagoras' theorem, that is x squared plus y squared equals 25 squared. Now we can either rearrange this for x equals in terms of y, and then square root, and we can ignore the negative because obviously x will be positive because it's the length, or we can use implicit differentiation. Now, to use implicit differentiation on this one, because we are actually going to be differentiating in terms of y to get dx dy, anything with an x will need to be multiplied by dx dy. So x squared will differentiate to 2x times dx dy, y squared will differentiate to 2y, and 25 squared will differentiate to 0. We can now divide by 2 and rearrange to get x times dx dy equals -y, and so dx dy equals -y of x. Now we have an equation for dx dy. We can substitute that back into our dx dt equation to get -y over x times by dy dt is -1, giving us just y over x. Now we know that x is 7 already, and we can use our Pythagoras theorem equation to find y. We're told that x squared, so that is 7 squared, plus y squared equals 25 squared. So that means that y squared equals 25 squared minus 7 squared, or 625 minus 49. So y squared equals 576, i.e. y equals the square root of that, or 24. Technically plus or minus, but since y must be greater than 0, y equals 24. Now I have my y and my x. That means that dx dt equals 24 over 7. Units are feet per second. Feet per second. Now in terms of our sign, does it make sense? Well, when the ladder is slipping down, y is getting smaller, and so it makes sense that dy dt is getting smaller, and so it's negative. Y is getting smaller, so it makes sense that dy dt will be negative. When it's slipping down, x is actually increasing in size, which means it makes sense that dx dt will be positive. A spherical balloon has been blown up at a rate of 5 centimeters cubed per second. Calculate the rate at which the surface area of the balloon is increasing when the radius of the balloon is 10 centimeters. So straight away, we need some formula. Volume of a balloon, well, V equals 4/3 pi r cubed, and surface area of a balloon, S equals 4 pi r squared. Those are both in your formula sheet. We're told that the volume is increasing at 5 centimeters per second, so that means that dV dt is equal to 5, and we want the rate at which the surface area of the balloon is increasing. So that's ds dt is what when r equals 10. So, same as before, we want an equation for ds dt. Well, ds dt equal to ds over something times something over dt, and we'll fill in what we know. We know that we have a dv. So we know dv dt, we just need this. Now typically that means we need an equation for v in terms of s or s in terms of v. Now looking at our equations, that's not so easily done. I could maybe for the s equation rearrange it for r, then take the square root, then plug that square root and cube it into the volume equation, but that's quite complicated. And so in this scenario we have to do an extra step. I can also now notice that both v and s are in terms of r, which means I can differentiate them both in terms of r. Looking at ds dv, we can do the same as we did before. That's ds times something over dv. And since I know they can both be differentiated in terms of r rather easily, we can sub dr into here, giving us a final rates of change equation of ds over dr times dr over dv times dv over dt. And you can get this sort of equation in your exam, and it's sort of identifiable because the derivative equation that you want to find will be quite hard, but if you split it up into a further variable, it makes it simpler. So let's go and find some derivatives. ds dr's first, so let's differentiate s. Rewrite that equation again, 4 pi r squared. ds dr is equal to 8 pi r. dr dv, well I think it's easier to find dv dr and then flip it. Rewrite the equation for volume again, 4/3 pi r cubed, differentiate, dv dr equals, timesing by 3, that gets rid of the third, so we get 4 pi r squared. Interestingly, the derivative of the volume of a sphere gives you the surface area of a sphere equation. Now that means that dr dv is 1 over 4 pi r squared. Meaning we have an equation now that this is 8 pi r times 1 over 4 pi r squared times dv dt, which is 5. Simplifying, the 8 and the 4 will cancel to a 1 and a 2. The pi's will simplify. This r and one of those will cancel, giving us a very simple equation of 5 times 2 over r, or 10 over r. We know that r is 10, so that means that ds dt is equal to 10 over 10, or 1 centimeters per second. Finally, a funnel in the shape of a cone has been emptied of fluid at a rate of 12 centimeters cubed per second. The height of the funnel is 20 centimeters and the radius at the top is 4. How fast is the fluid level dropping when the level stands 5 centimeters above the vertex of the cone? Okay, let's draw a cone. Now which way will it be? It is a funnel, so it's going to be this way. There's our cone, and it has some fluid in it. Let's just draw fluid. There it is. It's been emptied at a rate of 12 centimeters cubed per second. So that means it's going through the bottom of the funnel and it's dripping out. In terms of what actually is happening here, the funnel is 20 centimeters. Let's put that in. Height is 20, and the radius at the top is 4. we want to know how fast the fluid level dropping. Now the fluid level, that's indicating that we're talking about the height of the fluid. So that there is h, and here is the radius of the fluid. Let's give what we know. We know that it's been emptied of fluid, so the volume is going down per time, and since it's been emptied, it will be -12. We want how fast the fluid level, well that's the height, so that's dH dt, is what when h is 5. Okay, let's try rewrite an equation for dH dt. That's going to be dH over something times something over dt, and we know it's v, so dv dv. Okay, so we need an equation for h and v. Well, the volume of a cone, that equation, is 1/3 pi r squared h. That is now in terms of two variables. We only want it in terms of one. So we need to find an equation that joins r and h. Well, we have a similar triangle set up here. We'll draw it outside. We know that this is 4. This is r. This is h. And the whole thing is 20. So we already have all the common dimensions of the small triangle and the big triangle. That gives us, if we look at the height dimension, h over 20 will equal the base dimension r over 4. Which means that h equals, if we times by 20, 20 over 4 is 5, so that's 5r. Now we want dh dv, which means we want to swap out r squared in terms of h, and so r equals h over 5. Substituting that into our volume equation, we get v equals 1/3 pi times r squared, that's h over 5 squared times height, which expands to 1/3 pi times h squared over 25 times h, or pi h to the power 3 over 3 times 25 is 75. That is our volume equation. We can now differentiate that. dv over dh is 3 pi h squared over 75. Now 3 75ths, they both divide by 3, that is 1/25th. So that is pi h squared over 25, which means that dh dv, what we actually wanted, is 25 over pi h squared. So that's a lot of work to get that, but we got there. Now we know what dh dv is and what dv dt is, which means we can put this back into our equation. We have 25 over pi h squared times by, and dv dt from the equation was -12. Bringing those together, 25 times 12 is 300. So we have -300 over pi h squared. Now when h is 5, we've got -300 over pi times 5 squared is 25. Giving us -12 over pi centimeters per second. Now, does it make sense that it's negative? Well, the height is decreasing, so you'd expect it to be negative.